Okay, my name is Moseni, and I'm working on constructing mathematical and statistical model for EEG analysis at University of Technology, Sydney, UTS, with Professor Louise Ryan and Dr. Stephen Woodcock. So electroencephalogram, or EEG, is the bioelectrical activity of neurons, the brain cells, that it can be collected either from the scalp, the surface of EEG, as you can see. So there is no age limit. EEG can be collected either from kids to 99 years old or older, if they're interested. Or also it can be collected from like by a surgical implantation of electrodes on the surface of the brain, or even from deeper side of the brain. So as you can see on the right side. Surprisingly, the clarity of signals are very, very similar, because signals are very important, especially for some neurological problems like epilepsy. So there were so many studies that they compared signals from the surface EEG or the IEEG. So the similarities, the clarity of signals are very, very similar. So the application of EEG, it is either, so what I'm working on, there are so many applications for EEG, but what I'm working on are sleep and detecting seizures in epilepsy. So for sleep, you can see there are so many electrodes there involved. So they're collecting signals from the surface of the brain, also collecting signals from eye movement, muscle movements, heart or ECG, and also the respiratory signals are collected. And what I found that's very interesting, the correlation between EEG and ECG, so that they are kind of related. So we can map ECG to EEG, and then we can do the reverse engineering. By ECG, we can predict EEG somehow. So ECG is the electrocardiogram. What is very important in EEG, basically EEG comes with lots of artifacts. So as I said, so there are ways that you basically place electrodes on either surface of the brain or inside the brain. But the problem is, the very, very big problem with EEG is artifacts. So artifact, it can become, it can appear because of the movement or faulty equipment, or like a sweat surface is called sweat artifact, as you can see in the on the screen. So what is important to detect EEG by machine is to need to detect artifacts, take them out, and when you take the artifact out, so there would be a gap. So I need to find a way to basically predict the signals, the missing signals, and replace them. So that would be very helpful to basically, if we achieve that, we can train the machine to do the real-time EEG analysis. So that's what I'm planning to do. What I'm planning to do is to basically get to the point that either be able to predict EEG for sleep analysis, or for seizure detection in epilepsy. So if we can detect seizures, like predict seizures, we can basically save lives. It's very critical. Like 5 minutes would be very, very critical. There are so many different features on EEG that I would like to extract at the moment. Well, sorry, I just I lost the plot. I should have told you that I'm working on in the field of sleep analysis. So I have worked with so many sleep studies. So in sleep studies, like the knowledge that we have at the moment about EEG is very limited. Like we basically go through the sleep staging. What I mean by that is like if the patient is awake or asleep, and if the patient is asleep, is which stage of sleep is it? Is it the stage 1, which is a very light sleep, or stage 2, that is a transitional sleep, or stage 3, or a slow wave sleep, or dreaming, which is a REM sleep, rapid eye movement sleep. So what you can see here is basically a stage 3 sleep, and here is a stage 2 sleep. And this one is basically if we get rid of the artifact, it can be either stage 1 or stage 2 of sleep. So definitely the person is asleep here. So what I really would like to do is to basically go through the EEG, define using the mathematical and statistical model to go through different epochs of EEG. So it can be from the windows of 2 seconds to 15 seconds, and find out if there is any similarities or patterns in EEG that I can predict or I can detect. And I'm using machine learning. Hello?
We can still hear you, Ryan.
Oh, okay, great.
Yeah, just
talking to myself.
Last minute. Yeah.
Yeah. Yeah. So that's the sleep. Yeah. So taking out. So yeah, taking out the artifacts are very important. So need to take out the artifact and basically see what's happening. At the moment, there is no any application in the world that can basically go through the EEG and do the live detection accurately. And then if I can do that, so, and also there is another part of my my PhD is basically would collect the signals non-invasively. So from the ECG, I would plot back to EEG, and then I can basically read the EEG, and if there is any seizure, I can predict that. So that would be the outcome of my PhD, hopefully. So if there is any question, I'd be very happy to answer.